This lecture is going to look at section 2.2 of the book, the inverse of a matrix. So what is a matrix inverse? Matrix inverses, we're dealing with square matrices. So n by n matrix. We say that a matrix is invertible if there is something we can multiply that matrix by to get the identity. So in other words, if there's a matrix B of the same size, n by n, and for it to be an inverse, AB equals BA, which equals the identity. So when you're dealing with inverses, the order of that you multiply them by doesn't matter. You always come back with the identity. We say that this is the inverse, and we denote it by a to the power of -1. That's called A inverse. So for example, if A is that matrix and B is that matrix, try multiplying them together. You'll see that A times B is the identity and B times A is the identity. That is an inverse. An alternate note, or sometimes it's said that if you have a non-invertible matrix, sometimes that's called a singular matrix. And if it's invertible, sometimes it's called non-singular. I'm going to tend to use invertible and non-invertible terminology, but singular and non-singular also are used to mean non-invertible and invertible respectively. Theorem 4. If we're dealing with a 2 by 2 matrix, a very small square matrix, there's a quick way of getting the inverse. If our matrix is like that, and we have this property, AD minus BC is not equal to 0, we can very quickly get the inverse with this little formula. This number here, the AD minus BC, is called the determinant of A. You denote it by det of A. We are going to be seeing a lot of the determinant and for bigger matrices. But for now, we'll just introduce the term determinant, and it gives us a quick way of finding an inverse of a 2 by 2 matrix. Theorem 5. If we have an invertible n by n matrix, and we are trying to solve AX equals B, if we know the inverse, there's another way of solving it. X equals A inverse times B. So up until now, if we were trying to solve AX equals B, we put it into an augmented matrix and solved it. If we have the inverse, we have a quick way of solving it with a matrix multiplication. Why is that? Well, suppose we have that A is invertible and we know what the inverse is. We start with AX equals B. Well, A inverse is just another matrix, and if we know what it is, we can multiply both sides of that equation on the left side by A inverse. One of our rules of matrix multiplication says that when you have a matrix times a vector, you can multiply the matrices first and you come out with the same answer. So that third line is applying one of our properties of matrix multiplication, just saying you can bracket different places. But we've been told that A inverse is the inverse of A, so A inverse times A is the identity. So we just replace that. But the identity times any vector is just that vector itself. So the x that we're looking for, the vector x, is just equal to A inverse times B. What we have here is we have a proof of that theorem. A very quick and simple proof using the properties of matrix multiplication that we saw in the last lecture. So for example, if we have the matrix and we're told that that's the inverse, and we want to solve this system of linear equations, well, we are looking for the solution to 1, 3, 2, 5 times x1, x2 equals 4, 3. If we know the inverse, we know that x1, x2 is equal to the inverse, minus 5, 3, 2, minus 1, times 4, 3, and we can very quickly solve that. That gives us minus 20 plus 6. It gives us 12 minus 3 over here. And when we add them up, we get minus 14 and 9. There's our solution. So when you know the inverse, doing matrix multiplication or matrix vector multiplication is very quick and easy. Doing the row reductions is computationally much more intensive. It takes a lot longer time. If you know inverses, solving systems of linear equations is much faster. The catch is that calculating an inverse, in most cases, is not a quick and simple thing to do. It is itself computationally expensive. So theorem 6, 3 points for theorem 6. If we have an invertible matrix, then that inverse is also invertible, and the inverse of the inverse is the original matrix. Now, when you think of invertible matrices, we often think of it in terms of the reciprocal of a number. So if we're just talking about numbers, we will often say that the inverse of 3 is 1 over 3. Then 3 times 1 over 3 is 1. The inverse of a matrix is kind of similar to that. So you kind of get a lot of the same flavor with it. If A and B are square invertible matrices, then so is AB. So in other words, if you have two invertible matrices and you multiply them together, the matrix that you get is itself invertible. And the inverse of that is equal to B inverse times A inverse. Note how the order of the matrices change when you take an inverse. Okay. This again has a similarity to when you're dealing with numbers, but when you multiply matrices together and then take the inverse, you can do the inverses separately, but you have to change the order. This is very similar to what we saw with transposes last time. When you take the transpose of a product, it's the product of the transposes where the order is flipped. Same idea with inverses, and you have to flip that order. Third one is if A is an invertible matrix. Here we're combining the idea of transpose. The transpose is also invertible when you flip the rows and columns. And A transpose inverse is equal to A inverse transpose. So in other words, if you have inverses and transposes, you can do them in whatever order you want. You're going to come out with the same answer. Okay, that's the idea of inverses. Now we're going to go to something called an elementary matrix. We saw elementary row operations. So we had 3 things for elementary row operations where you can flip rows, you can multiply a row by a product, or you can add the product of a row to your row. Those were the 3 elementary row operations. And we saw how we can use those to row reduce a matrix down to a matrix in reduced echelon form. What if you start with an identity matrix? If you have an identity matrix and you apply a row operation, an elementary row operation, the matrix that you get is called an elementary matrix. So here's 2 examples. If we start with a 4 by 4 identity matrix and apply S times row 2 becomes the new row 2. That's an elementary row operation. You're multiplying a row by a number, by a scalar. You end up with that. This matrix is an elementary matrix. Another type of row operation was when you take a multiple of one row plus a second row and replace that second row. That is an elementary row operation. If you do that to the 4 by 4 identity matrix, you come up with that. This is an elementary matrix. So elementary matrices you get from applying a single elementary row operation to the identity matrix. Theorem 7. This theorem says that if you have an invertible matrix, then you are guaranteed that you can do row reductions to bring that matrix to the identity through elementary row operations. And the other way around. If you have a matrix that you can bring to the identity through row operations, that means it is going to be invertible. So this is bringing together a couple of ideas we've seen, the ideas of invertibility and all of those processes around elementary row operations and row reducing a matrix. Invertibility is the same as being able to do row reductions to the identity matrix. But this theorem actually even goes one step further. It says that if you can do these operations to bring a matrix down to an identity matrix through elementary row operations, remember what all those operations are, all the row operations, do the same row operations on the identity matrix, what you're going to come out with is the inverse matrix. So this is a fairly deep theorem, but it's a very important theorem for a couple of reasons. One is that it brings together two ideas we've already seen. It says that at some level, these are the same ideas. They say the same thing. The second important thing about this is it actually gives us a procedure for finding the inverse of a matrix. So let's see what this means through an example. Let's take this matrix and use this theorem to see how we get the inverse. So the theorem says that the inverse exists if we can row reduce down to the identity matrix. So let's see if we can do that first. Start off with our original matrix. Now we're going to row reduce. So we are going to start by taking 1/2 of row 1 is the new row 1. I'm just going to get a 1 at the start here. Gives us that matrix. Now let's get rid of the number in column 1. So let's take row 2 minus 3 times row 1 is the new row 2. We get 1 negative 3 over 2. Then on the second row, we get 0 and negative 1/2. Now let's take this and we are going to, let's get a 1 in the bottom right corner. So we are going to do negative 2 times row 2 is the new row 2. Gives us 1, negative 3 over 2, 0, and 1. Now let's get rid of that final number, the top right corner. If we do row 1 plus 3 over 2 R2 is the new row 1, we get 1, 0, 0, 1. We get the identity matrix. So we have the identity matrix from our theorem. That means that it's invertible. Now, what is the inverse? The second part of the theorem says that if we want to get the inverse, we take those same row operations and we apply them to the identity matrix. So for this, we are going to start with the identity matrix and we're going to apply the same row operations. So the first row operation we did was 1/2 row 1 is the new row 1. Gives us 1/2, 0, 0, and 1. The second row operation we did above was row 2 minus 3 row 1 is the new row 2. We get row 1 stays the same. Then we get minus 3 over 2 and 1. Third row operation we did was negative 2 row 2 is the new row 2. So that gives us 1/2, 0, 3, and negative 2. And the final row operation we did above was row 1 plus 3 over 2 row 2 is the new row 1. What does that give us? That gives us 5, negative 3, 3, -2. So this is equal to A inverse. Check this out. Take A inverse, multiply them together. You'll see you end up with the identity matrix. So theorem 7 gives us a way of not only identifying if a matrix has an inverse, but it actually goes one step further and tells us exactly how to calculate that inverse. We did it for a simple example of a 2 by 2. It works for any size of square matrix. Thank you for your attention for this lesson.